So I just met this girl. You may already know her, but she's really excited because she just got her first pair of ice skates. And she's wandering around, Harold in the Purple Crayon style, and she comes to this really cool place to ice skate, and it looks like this. It goes, woo, and it's ice on a hill, and it goes like that, and then it goes, woo, and it goes back up to where she started. So she liked that a lot, and she's gonna go again down it, and she's gonna go this direction. Whee! And can you tell me where she's going the fastest as she's skating? And then she slows down as she gets to right here because there's no friction. So she just, I guess she's just converting some potential energy that she's got right here into some kinetic that she's got right here. And then she gets a little bit of that kinetic sacrifice to getting up this tiny lump right here. And she goes back down and converts some more back into kinetic. And then she takes that kinetic and turns it all back into potential right here when she, excuse me. Well, I guess that's the end of that. Just kidding, when she's stopped. So I'm gonna say that right here is her total energy. I'm gonna call that total E. And I'm gonna actually argue that the path of the ground for this happy skater is a graph of her gravitational potential energy. Because the cool thing about the ground is it's a graph of height. If you look at this, we could say that it's a graph of y versus position as we move along the ground, and y is height. And the cool thing about height is that gravitational potential energy depends directly on it. So with a weighting factor of the weight of this skinny, pretty, happy skater is that she is converting her potential energy exactly as her height is changing. So when her height is the smallest, right here, she is going the fastest. It's very reasonable. So what we can say is that at this point, all of her energy is gravitational potential energy. So let's call this location, what do you want to call it? You want to call this location 0 for H? Sure, we can call that H equals 0. And over here we can call it H equals H max. And then at the bottom, her energy is exactly 0 in potential. But what is her energy in kinetic? Well, we know me I is me F. And without getting into the details of that statement, we can at least argue that initially her energy was mgh max. And so finally, her energy here must also be mgh max. So we can identify that as the same thing as 1/2 mv max square. And we could find v max, right? Let's find out the fastest that she's possibly going. We can cancel out the m's and we can make the statement that g times h max is equal to 1/2 v max square, and the fastest she's ever going is root 2gh max, and that is her maximum speed. Okay, so some other things we can say about this situation is if she has no friction and she's skating, this point right here where all of her energy turns into potential is where she will turn around, right? As she continues to do this, she's going to turn around here each time, and we can call that point a turning point. Well, let's just label that. Here's a turning point. We have to write it out, otherwise it looks like toilet paper. Turning point here, and there's a turning point right there. And remember though, this is a graph of potential energy as a function of distance. So let's make a more typical graph of potential energy. Let's say, the graph of a mass on a spring's potential energy. We can make that graph look like this. If this is our potential energy, elastic, we could attach this happy skater onto a spring. And when we pull her out this direction, there's a correspondingly large force that's pulling her back the way she came from. So she would go boing, 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 back between this equilibrium location for the spring. And this, I guess, would be the displacement away from equilibrium. And her energy, her elastic potential energy, is just 1/2 k times x squared. So as k gets bigger, this graph is going to get, well, let me draw up, first of all, this is a parabola. Everybody get a what on this being a parabola, 1/2 kx squared? Dang it. There's that bell again. Watch this. I'm going to give you a parabola, as pretty as I can make it. Look at that. That was a dang nice parabola. Okay, so it's symmetric and it's quadratic. It's not exponential, it's quadratic, and it goes like x squared. If k were bigger, this graph would have to be more like this. It would be steeper if k were bigger. And if k were smaller, the graph would be further out that way. This is for big K, and then out here would be for little k. But this is the graph that I want to consider, this one that's in bold red right now. So let's give the skater some energy. So we'll pull her out here, we'll go, and we'll pull her out here, and then we'll let go. So right now, she is completely still, and so this is the energy that she's going to be starting with, and we could call it, well, I guess we could identify this energy. We could call this x max, and the energy at the start, well, we could actually say that this is E. This is her total energy at the start. Guess what? Her energy is going to be conserved. So the energy at the start is going to be U max. That's her maximum potential energy, and that's equal to 1/2 kx max sucker square. And so this energy will be conserved, and we'll find out how much energy she has when she gets to there, because it will be exactly the same amount of energy. Notice this is her total energy, and it never changes. So if you want to know how much potential energy she has as a function of location, you just look at this graph of potential energy. I mean, that means that, like, take this position of our poor skater. If she's right here, right, then her potential energy is right there. That is her potential energy at that instant. Let's call this x1. This is potential energy 1. How do we find her kinetic energy at that point right there? Well, we make this simple statement. We say that total energy at location 1 is kinetic energy at location 1 plus potential energy at location 1. In fact, also the total energy at location 1 is equal to the total energy at the start. Interesting, because she's not losing energy and she's not gaining energy. So I want you to consider that when she's starting right here, she has what we'll call U max. That's the energy that she has right there. And then her kinetic energy is 0. So what do you know about this distance? What do you know about that distance? Well, it's U max, right? And it's also E start, and it's also 1/2 kx squared. All this stuff, that energy is a fixed level as she transfers her energy from, let's see, potential here to all kinetic here to all potential there. So this energy that's above the line, this energy right here must be her kinetic energy at location 1. And in fact, at any position, we can find the relationship between her kinetic and potential energies by the ratio of this line. What's above the line to what's below the line. Let's take another position where it's a little bit more extreme. She's probably going pretty fast right here. Let's call this x2. I'll try to stay consistent on colors for you. This is x2, and her potential energy at x2 is very small. This is u2 right there, and her kinetic energy is correspondingly larger at position 2. This is her kinetic energy at location 2. All right, so at all times, this statement is true. Energy total at any location is equal to kinetic energy at any location plus potential energy at that same location. And since it's conserved, it's equal to the energy at the start. And that means that it's equal to 1/2 kx max square. Of course, it's also equal to, all the time, it's going to be equal to the maximum kinetic energy at the center, because that's where all the potential has converted into kinetic. So then we're going to have that's equal to also 1/2 mv max square. And we've got this turning point here and this turning point here, and that's where her energy is completely potential, and that's why she turns around. So she goes Here she goes. Whee! It slows down and stops it, turns around and it goes. Whee! Okay, that's enough of that. Let's say our skater goes exploring, but she's now no longer looking at a side view of the hill which she's approaching, but in fact she sees a hill that looks like this in a topographical map. Very interesting. As she comes up to this hill, what would be the easiest way for her to climb this climb this hill if it's a topographical map? Should she approach from this direction? What do these lines mean? What the heck's going on? Let's say this is 1,000 meters. Oh boy, this is going to be a really steep hill. Let's not make it quite that steep. Let's say that's 100 meters, and this is the ocean or something. Yeah, we need some waves, some purple waves here. Yeah, this is the ocean out here. So she's been ice swimming out here, and she comes up to this island, and she notices that this is 200 meters, and this is 300 meters. This means that this line everywhere along it is at an altitude above sea level of 300 meters. So this is 400 meters, and this is 500 meters, and this little peak right here must be at 600 meters above the sea. So you could argue that going this direction would mean that over a very short time she'd have to cover great vertical distance to get up. But it might be easier for her to ice skate over here, ice, water, skate, ocean, something, to get up here and go very gradually up the hill. The reason is, if we argue that height is gravitational potential, height is, I need a bold color for is, here we go, height is gravitational potential. That means that, I want you to really soak this idea in. I'm saying that mgh is very, very, very similar to just h. So assuming you know the mass of the girl, you can say that a graph of where she is in height can tell you her gravitational potential energy. I think that's a small leap conceptually. Let me know if there's any trouble with that. This graph is a graph of height as a function of now x and y. So it's sort of a three-dimensional graph because she can come at this mountain from over here, and she can increase her gravitational potential energy very gradually, or she can come at the hill from over here, and she would increase her gravitational potential energy very dramatically. Okay, so we could, increasing gravitational potential energy reminds me of a derivative. It's talking about how quickly something is changing. And so without regard for x and y, I'm just going to say that this might be du dx, the change in gravitational potential energy with distance. And over here, du dx right there, is smaller. So which of these two is, shoot, I already told you. Would you believe that these are derivatives of energy as a function of distance? And do you know what the derivative of energy as a function of distance is? Let me see if I can convince you that you already do. You know that work is the integral of force over distance. And you also know the fundamental theorem of calculus, which says that if you take a derivative of an integral, you get back what you had. So let's take a derivative of an integral. We'll say that this work that's done to lift someone against gravity is actually the change in gravitational potential energy. So we'll say she's starting at 0. We're going to call it sea level, h equals 0. And we'll say that we want to know, we're going to just call that u right there. I want to know what du dx is, but that means I'm taking d dx of the integral of f dot dx. Check this out. This says take force, integrate it over x, and then differentiate it with respect to x. And you're going to get back, you guessed it, force. So the derivative of potential energy is force, and can you imagine that this takes a larger force against gravity to get up the hill rapidly than it does to get up the hill slowly? Of course it does. The hill is steeper. So a greater component of the force that she exerts has to be exerted in a vertical way, so she'll have to exert a large force to get up the hill here and a small force to get up the hill here. In fact, if she takes a greater distance and a smaller force, she will have the same change in energy because work is the integral of force over distance. So she can have big force and small distance. That's this way of climbing up the mountain. Or she can have small force and big distance. That's this way of climbing up the mountain. And either way, she'll get from sea level to the top of the mountain. So this, in general, helps you to understand, I hope, helps you to understand an equipotential. And that means that every line around here is an equipotential. But notice that these lines that are normal to the equipotential show the direction of force. And we'll come back to this in electricity and magnetism. It's a very important idea that at a right angle to equipotential is where the force is. In fact, we've been talking about this poor girl trying to climb the mountain. Let's instead consider she's on the mountain. And if she goes a little bit in any direction, she'll experience a force that will encourage her to go directly down the mountain. Think about what directly down the mountain means. When she's right here, directly down the mountain means at a normal direction to her location, which is at a normal direction to the equipotential. Right here, if she's going down the mountain, she's going to go that direction because gravity points normal to the gravitational equipotential. Right here, the force on her is that direction. Right here, the force on her is that direction. And right here, the force on her is to get out into the water over there. Very interesting. Ask me some questions about this. This is some pretty heavy mathematics, but it's going to be really useful for us. I'm going to draw these forces that she would feel if she were at any of these locations. Do you believe it? That the force on her will be exactly encouraging her to leave the mountain? Think about it. If you're on a hill, the force is directly down the hill, and these arrows, the black arrows that I've drawn, are always directly down the hill. That's what it means to be normal to an equipotential. And I should write the word equipotential here so you know what I'm saying. Goodbye. So I just met this girl. You may already know her, but she's really excited because she just got her first pair of ice skates. And she's wandering around, Harold in the Purple Crayon style, and she comes to this really cool place to ice skate, and it looks like this. It goes, woo, and it's ice on a hill, and she, excuse me. Well, I guess that's the end of that. Just kidding, when she's stopped. So I'm gonna say that right here is her total energy. I'm gonna call that total E. And I'm going to actually argue that the path of the ground for it goes like that, and then it goes woo, and it goes back up to where she started. So she liked that a lot, and she's going to go again down it, and she's going to go this direction. Whee! And can you tell me where she's going the fastest as she's skating? And then she slows down as she gets to right here because there's no friction. So she just I guess she's just converting some potential energy that she's got right here into some kinetic that she's got right here, and then she gets a little bit of that kinetic sacrifice to getting up this tiny lump right here, and she goes back down and converts some more back into kinetic, and then she takes that kinetic and turns it all back into potential right here, when this happy skater is a graph of her gravitational potential energy. Because the cool thing about the ground is it's a graph of height. If you look at this, we could say that it's a graph of y versus position as we move along the ground, and y is height. And the cool thing